So a, so a free Dirac fermion in 1 plus 1D has two components, psi left and psi right. Each one of them is a complex Weyl fermion. So psi left is a one component complex left Weyl fermion. Psi right is a one component complex right moving Weyl fermions. These are two different kinds of Weyl fermions in 1 plus 1D. They are distinct representations of the 1 plus 1D Lorentz group. And the Lagrangians is given by this. The left mover and the right movers, they don't talk to each other. And this is there's no interaction, no mass so far. Okay. Now, what are the symmetries of this model? Obviously, there's a vector U1 symmetries that rotates both the left movers and the right movers by the same phase. There's also an axial U1 symmetry where you rotate the left mover and the right mover by the opposite phase. So the relative sign difference between these two is crucial. In fact, a better way to write the symmetry is to think about a U1 left that only rotates the left movers and a U1 right that only rotates the right mover. But for reasons that will become clear later on, it's better to organize the symmetries into the vector and the axial one. Now there's a Z2 quotient between the two U1s. What this means is that if you take theta to be pi, for the vector U1, that acts in the same way on the fermions as you take the axial one with theta equals to pi as well. In both cases, that Z2 element just flip the signs of both the left mover and the right mover. Since they share the same Z2, the global form of the group has this Z2 quotient. It's not terribly important for the talk today, but it's good practice to keep track of the global form of the global symmetry. All right. So we would like to realize this simple free fermion model on the lattice. And today we are going to work with the Hamiltonian lattice formalism. I will comment on the Euclidean one, which many of the people in the audience have also worked on later on in the talk. So in my setup, time is continuous, and the time evolution is specified by the Hamiltonian, but space is discrete. And in part one of the talk, the space is going to be a periodic circle. In part two, it will be a two-dimensional spatial lattice, typically taken to be a torus, and so on and so on. So this is our space in part one. You have L sides, and on every side, there will be some local degrees of freedom. And we will assume periodic boundary condition. We also assume the number of lattice sides to be even for simplicity. Now, in the continuum, the dispersion relation for a right-moving fermion is just that the energy is equals to the momentum. For a left mover, then energy will be equal to the minus of the momentum. Now, if you want to realize the continuum fermion on the lattice, the energy of the states on the lattice is necessarily periodic in momentum as you go from one end of the Brillouin zone to the other end. Now, what's the simplest possible periodic function you can write down? It will be a sine function. If you look at this sine function, near k equals to 0, this is where the low energy modes live at. This is near k equals to 0, sine can be approximated by its argument, and you recover the dispersion relation for right-moving Weyl fermion. But since the sine function has another end at k equals to pi, this is halfway through the Brillouin zone. At the other end, you necessarily have a left-moving fermion. So the upshot is that in 1 plus 1D, the left and the right fermions must necessarily come in pairs. You buy one, you get the other one for free. And this is known as the fermion doubling problem. Okay. So naively, if you want to realize a Dirac fermion on the lattice, you would put two complex fermions per site. This is because a continuum Dirac fermion has two complex components. So the most naive regularization will instruct you to put two complex fermions per site. But because of the doubling problem, if you do put two complex fermions per site, you will end up getting two Dirac fermions in the continuum. And that's twice as much as you desire. In 1 plus 1D, there's a simple resolution to this fermion doubling problem. You simply place one complex fermion on every lattice site instead of two. So I'm going to denote this complex fermion per site by Cj. Okay, so at every site you have Cj and Cj dagger, and they obey the standard anti-commutation relation. Now, the Hilbert space, this complex fermion axon, is a two-dimensional Hilbert space. In fact, locally, you can bosonize it to a qubit. Now, since we have L site, the total Hilbert space is 2 to the L dimensional. And the Hamiltonian we're going to work with is the famous staggered fermion Hamiltonian, discussed by Banks, Kogas, and Susskind in the 70s. And this is really the simplest possible Hamiltonian you can write down, enjoying some of the symmetries we want. First of all, we would like to demand the U1 vector symmetry that rotates the complex fermion by a phase. So everything has to come in pairs of C dagger C. And second, you write down the nearest neighbor interaction. And to make it Hermitian, you have to have two terms. So this is literally the simplest Hamiltonian you can write down. And that's it. I see there are some questions. I somehow couldn't hear anything so far. Okay, I'm waiting for the mic.
Hi, Shu-Heng. This is Sung-Woo.
Yeah,
So since I'm not familiar with this question, let me ask a question at the risk of being dumb.
no
So
worries.
yeah, right. If you use a sign regularization, like, yes, I can see that you always have this pair, and then probably you said that instead of putting two Weyl fermions, let's just put one because anyway, one already provide you two of them. But
Right.
naively, one arises at with respect to k equal to 0, the other arises when k equal to half a period. Do I have to worry about that fact or?
Worry about which fact?
The fact that one mode arises with respect to centered around the k equal to 0 point,
Ah,
and the other one
ah.
arises near like a finite k rather than k close to 0.
Oh, I don't think you have to worry about it. It's more like a feature rather than a bug.
Oh,
So
okay.
that's in space, right? So it doesn't mean that the fermions are, so it's quite common that if you start with a lattice model, you have low energy modes at different regions in the Brillouin zone, but they will all contribute to your low energy effective field theory.
Okay. And second related question is, I guess we don't have a better regularization that doesn't have a pairing problem, doubling problem.
Well, so
I'm just checking whether it's an artifact of the choice of regularization rather than the intrinsic problem.
I will say a little bit about that later on, but indeed here, as far as the quantum field target quantum field theory is concerned, we get it, right? We aim to get one Dirac fermion, and I'm going to argue that the one I wrote down does give you a single Dirac fermion.
Okay.
So as far as that goal is concerned, we have achieved the goal.
Okay. Great.
Level
Thanks.
two,
Uh-huh.
if the question at the second level is more subtle. It's about realizing the chiral global symmetry.
I
And
see.
later on, I will refer to some general no-go theorem to justify what's the best you can do.
Okay. Thanks.
Mhm. Was there another question? All right. If not, let me continue. Okay, so this is a very simple, this is really the simplest possible lattice fermion Hamiltonian you can write down. Its nearest neighbor. You can add many more terms, but this one will be a natural starting point. As I already said, the continuum limit is one free massless Dirac fermion. It's non-chiral. It has a left mover and a right mover. So there's no fermion doubling problem. But as I commented earlier, the question we would like to have is, can we realize all the chiral global symmetries of the continuum theory on this lattice model? Now, the U1 vector symmetry, that one is easy. That one just rotates all the complex fermions Cj by a common phase. And it is manifestly a symmetry of the Hamiltonian. But where's the actual U1 symmetry? This model doesn't seem to have a second U1. So that's the main question we would like to ask. Now, it could be that the U1 axial symmetry is just not there on the lattice. It is quite common that the low energy effective field theory has more symmetries than its microscopic lattice model. Symmetries can be emergent. Well, but is that the case for this particular Hamiltonian? Furthermore, common law states that it's difficult, if not impossible, to realize the axial U1 symmetry on the lattice because there's an anomaly, to be more precise, a 't Hooft anomaly between the vector and the axial global symmetry. Now, this 't Hooft anomaly implies the following. It is the statement that the axial U1 symmetry is broken when the vector symmetry is gauged, and vice versa. Historically, this anomaly was first discussed by Schringer in 1959, and then there was a very nice paper by Ken Johnson in 1963 that really formulate this phenomenon in the language that we are now familiar with. So in equations, it means that if you couple your Dirac fermions to a U1 gauge field by gauging the vector U1 global symmetry, then the conservation equation of the axial current is no longer zero. Rather, it is violated by the electric field for the U1 gauge field of the vector symmetry. And this is the anomalous conservation equation from the Schringer anomaly. And as everyone is probably familiar with, this is captured by a one-loop two-point diagram in the continuum field theory. This you can view as the baby version of the ABJ anomaly in 3+1 dimensions, and it's much easier than the ABJ anomaly. ABJ anomaly is a triangle diagram involving 3 external legs, whereas in 1+1D it's just a one-loop diagram of only 2 legs. Now, perturbative anomalies, namely anomalies that are captured by perturbative diagrams, such as the Schringer anomaly, are particularly challenging to realize on a lattice with a fine-dimensional local Hilbert space. And that's the setup we have here. In our setup, on each side, we just have a two-dimensional Hilbert space. Having said that, I should comment that this anomaly can be realized, or to be more precise, its bosonized version can be realized on lattices where the local Hilbert space is infinite dimensional. And there was a very nice paper by Ting and Gattinger from a few years ago achieving this. And then there were some follow-up papers. This formalism is sometimes known as the modified Villain lattice model. But the key difference between that lattice model with the setup that I'm talking about today are, one, the model I'm talking about today is a Hamiltonian lattice model, whereas the modified Villain model is a Euclidean lattice model. This difference is not terribly important because the modified Villain model can also be turned into a Hamiltonian one. But the more important difference is that the local Hilbert space in the setup today is finite dimensional, whereas in the modified Villain it's infinite dimensional. All right. Now, so in this talk, which the part one of this talk, which is based on the first paper that I cited at the beginning of the talk, is we're going to discuss the realization of both the vector and the axial charges in this lattice model. So in the end, we will find two conserved charges, QV and QA. QV we already have, and the more subtle charge is QA. Both of them commute with the Hamiltonian, and in that sense, you can call it a symmetry. These are conserved quantity invariant under time evolution. This is a true statement for finite L. And you can literally write these conserved operators down. Furthermore, these two conserved charges, their eigenvalues, these are operator or matrices acting on your finite dimensional Hilbert space for any given L. And their eigenvalues are always integers for any L. And that is what we want. A U1 global symmetry should have integer charges. Otherwise, it doesn't generate a compact U1. So far it seems that this is all good news, and we seem to have realized some anomalous symmetry on the lattice without running into any issue. But there's always a but in theoretical physics. Here there's a price we have to pay. And the price we pay is that the vector charge and the axial charge actually do not commute on the lattice for a generic state. This is to be contrasted with the continuum where U1V and U1A form a direct product and their charges commute with each other. After all, in the continuum, these are just phase rotation, and phase rotations commute with each other. All right, so this is the punchline of part one of the talk. If there's no question, I will go into the details of the construction. Yeah.
So maybe can you tell us in advance what's the quantity appearing on the right-hand side of that commutator?
Um, I'm going to write it down explicitly. It's going to be some operator that's quadratic in the fermion. Um, it's an operator that also commutes with the Hamiltonian because it's made out of conserved quantities, but it doesn't have integer eigenvalues. And that commutator, namely the right-hand side of, more precisely, the right-hand side of this commutator, we can show that it vanishes in the continuum limit. But other than that, I don't have anything more illuminating to say about that charge. But perhaps it will become clear later on in the talk.
Okay, great. Thank you.
Yeah.
So at finite end, there is a Hilbert space, the finite dimension, and you can try to solve this commutation relation. And is it the only solution? QA and QB is the only solution, commuting with the Hamiltonian at finite L. Is there any other? So is there any other conserved quantity in this Hamiltonian? The QA and QB is only the Hamiltonian.
Oh, good. Good. So this is so far I'm talking about free fermion Hamiltonian. In fact, it has infinitely many conserved quantities. The lattice model is in fact integrable. But most of these conserved quantities, they do not respect locality in a nice way. QV and QA, as I will discuss later on in the talk, they are locality preserving operator. Namely, their associated unitary operator will map a local operator to a local operator. But beyond this QV and QA, there are also some other locality preserving conserved charges, and we will run into some of them later on. So the short answer is no. These are not the only conserved quantities of the Hamiltonian.
Hi. How do you define the locality on the lattice?
Yeah, I will talk about that, but maybe I'll just say it now. So by locality, I um I actually mean ultra locality. So if you start with, say, an operator that's strictly localized on a site, uh, what I meant by locality preserving operator is such that when you act on this on-site operator, the output is an operator that has a finite range span. So maybe the output span over 5 sites, but the span will not scale as you take the system size L to be larger and larger. So as long as the range is older 1, I will call that locality preserving. In this talk, I also don't allow tails. So I really meant ultra locality.
Thank you.
So you're saying that this QV and QA do not commute with each other. So it will generate another conserved charges.
Yes.
Is it local or non-local?
The conserved charges it generates, the little right-hand side of this equation is still local.
It's still local. So
Yeah.
is that do they make some kind of algebraic structure there?
Yeah, hold your thought. I'll definitely get to that.
All
That's
right,
the
thanks.
punchline. Yeah, so I lie a little bit. I haven't given away the punchline. Okay, any other question? Okay, let me proceed. Great. All right, so now let's go to the technical details. So again, the goal is to realize this axial U1 symmetry on the lattice. So how do we achieve that? Now let's go back to the continuum for a minute, and I'm going to note a very elementary fact. In the continuum, the conserved axial charge and the conserved vector charge are actually unitarily equivalent. And the operator that relates them is what I call a right-moving charge conjugation. So I denote it by CR. C stands for charge conjugation. R stands for the fact that this operator only acts on the right movers. So here's the definition. this charge conjugation conjugates the right-moving vial fermions to its dagger and vice versa, but it doesn't do anything to the left mover. Okay, so just some Z2 unitary symmetry of your continuum field theory is an honest to God unitary Z2 symmetry. And you can see that if you do a right-moving charge conjugation, you swap psi r with psi r dagger, and therefore flipping the sign here. And that's why the vector charge and the axial charge are related by this unitary Z2 symmetry in the continuum. Okay, it's a very simple group theoretical fact in the continuum. All right. Now on the lattice, we already have the vector charge. That's very easy to write down. It's manifest on the lattice. So all we have to do to obtain QA is to identify the lattice counterpart of this charge conjugation symmetry, CR. Okay, so that's our strategy. We have reduced the task of finding a continuous axial global symmetry on the lattice to finding a discrete symmetry on the lattice, which should generally be easier. But the question is how? How do we find the lattice counterpart of this CR? Now, in all three parts of the talk, we only have one trick. And that one trick is just to be real. We start with the complex fermion lattice model. And the trick is to decompose that complex fermion into two real fermions. So I'm going to write Cj, which is the complex fermions, as Aj plus Ibj, where Aj and Bj are two Majorana fermions per site. So they are self-adjoint operator. In fact, this is largely inspired by Kitaev's seminal paper on the Majorana chain. If you write the original Hamiltonians in terms of the real fermions, then it becomes this. This is just a two-line algebra. You see that the two real fermions don't talk to each other. And in the continuum limit, this just describes the two Majorana fermions. In the continuum, we also decompose the left-moving vial into two Majorana vial components. And similarly, the right-moving vials decompose into two Majorana vial components. So in total, you have four Majorana vial fermions, A left, B left, A right, B right. In the charge conjugation symmetry, flip the sign of only BR, right? Because CR tried to take psi R to psi R dagger. And to achieve that, you flip the sign of its imaginary part. So, which lattice symmetry only flips the sign of a single Majorana vial fermion BR in the continuum limit? Okay. Now, for anyone who has worked on lattice fermion, the answer by now should be clear. As I said, the Hamiltonian written in terms of the real fermions decouple. So we can just focus on the B Majorana fermions. If you focus on the B Majorana fermions, its dispersion relation is a sign function, as I alluded to earlier in the talk. Near k equals to 0, you have the left-moving vial fermion. Near k equals to pi, or k equals to L over 2 in this convention, you have a right-moving fermion. For those of you who are paying attention to the talk, you might be wondering why I call this left mover, this the right mover, even though this looks like the right mover. But there's a very annoying sign in the entire thing. But believe me, we really fixed the left versus the right in the paper carefully. And this is really the best convention. So the upshot is that don't pay too much attention on the left versus right. We got it straight. All right. Now, as I said, there's a left mover here and a right mover here. So what is the symmetry of this B fermion model that only flip the sign of this B right, but not B left? Naively, you might say, oh, what if I just flip the sign of the BJ lattice fermion? But that's not good. That will flip the sign of both B left and B right in the continuum. What we want is something that only flips B right. And the answer is given by a Majorana lattice translation. This operator I denote by TB. T stands for translation. B stands for the fact that this operator only shifts the Majorana fermion by one side. The B Majorana fermion by one side. But it doesn't shift the A Majorana fermion at all. Okay. Now, a translation operator, when you go to momentum space, becomes diagonalized and it acts by a phase. When this phase is close to this end of the Brillouin zone, it acts as +1. Whereas if you are halfway through the Brillouin zone, K is L/2, and if you substitute that into this phase, you get a -1. So the upshot is that the Majorana translation for the B fermion in the continuum limit become a charge conjugation symmetry that flip the sign of a single Majorana biofermion. Right. Is there any question up to this point? So far we have found the lattice counterpart of the charge conjugation symmetry.
Shu-Heng, here
Hi.
L is assumed to be even or L can be also odd.
Excellent question, and I can prepare for that. So let me actually show you my earlier slide where I did say L is even. So the short answer is yes. And when L is odd, it's a more interesting model. And as you probably know, that corresponds to inserting some defect in the continuum. But I have to be honest, we didn't analyze that model. So throughout, I'm going to assume L to be even. Was there another question? Yes.
This is not a question but comment. So I see that you are trying to use cursor to articulate and explain things. So we see a mismatch of the location. So it'd be useful if you actually say, I mean, if you can, like explicit, word or whatever, so that we can actually follow your explanation. So far, you're doing excellent job. I'm just letting you know that. Oh,
yeah, thank you. Yeah.
Which one are you pointing now? Just test.
Okay, let's see. So this is the B fermion. Does that make sense?
B J+1. Is that what you're pointing?
Yeah.
Perfect. Now it completely matches. Thanks.
Okay. There might be a lag. I noticed that sometimes. Maybe that was the reason. Thank you. Yeah, thanks for letting me know. All right, let me continue. Okay, so we have achieved halfway what we want. We have identified a lattice symmetry, the Majorana lattice translation, that goes to a right-moving charge conjugation in the continuum. So now what do? We just mimic the continuum relation here to define the following operator on the lattice. So we take our QV, the vector charge, and conjugate it by the Majorana lattice translation. So the vector charge, if you write it in terms of the Majorana fermion, it takes this form. I didn't derive this, but it takes you like 2 minutes to realize this is the case. Now, if you conjugate it by a Majorana translation only for the B fermion, you just shift the relative location between A and B by 1. So this is the key equation of the entire talk. This QA, I claim, is the lattice counterpart of the axial global symmetry. Okay, so now we have our guy on the lattice. We want to analyze its property. Now, first I claim that it goes to the continuum axial charge. That is just because TB goes to CR, and if you compare the two formulas, it shows that QA goes to the continuum QA. So what are the nice properties of this QA? First, it commutes with the Hamiltonian.
So, question.
Yes.
So
Yes,
if
please.
you rewrite these A and Bs in terms of complex fermions, maybe you have some C daggers, and CCs, which, break the complex fermion number conservation. So do they appear? Do they have to appear? Is that the answer?
Yep. Yeah, you're stealing my story. That's exactly why. This QA, if you write it in terms of the complex fermion, will contain some term that looks like CC or C dagger. And that's precisely why it doesn't commute with the vector charge.
I see. Okay.
All right. But before I tell you the bad news, let me first tell you the good news. So since QA is defined as this product, and since TB and QB are both conserved quantities, QA is also a conserved quantity. So it commutes with the Hamiltonian. It's a symmetry. Second, it is quantized. The reason is because QA is related to QB by unitary transformation, and unitary transformation doesn't change the eigenvalues, and therefore it also has integer eigenvalues. And that's why I give you a compact U1 global symmetry. Third, it's a sum of local terms. By local, I mean finite range. So QA here is manifestly written as a sum of terms where each term is only spans over two sides. And you can view the local terms here as the lattice version of the time component of the Noether current. If you have a U1 charge, the unitary operator is obtained by exponentiating this charge. So you write it as e to the I theta QA. And the way it acts on local operator is through this automorphism. So it maps the A Majorana fermion as psi j to the right-hand side. I think this addresses one of the earlier questions by what I meant this symmetries to be locality preserving. You see, it maps a fermion as psi j to a linear combination of the original fermion to its nearest neighbor. But this doesn't spread out. For any value of theta, it doesn't mix the original fermion to some fermion far away. So in this sense, this is locality preserving. When your L is a million, differing by one side is as if nothing happens. It's as if they're on top of each other. Okay. Now, as I said, the only thing you give up on is that QB and QA do not commute on the lattice, whereas they do commute in the continuum. Now, if they don't commute on the lattice, it was already asked, then what kind of algebra do they form? Let me talk about that. To that end, let me define something more general. Let me define Qn to be this expression. Recall when n is 0, this is precisely our QV. When n is 1, this is our QA. But now I have defined an integer family of them, which I call Qn. And this Gn is some quadratic fermion operator. Qn and Gn, for every n, they all commute with the Hamiltonian.
Sorry, Shu-Heng, so let me bother you one more time.
Yeah, please.
So yeah, if you can define QA and QV, I guess you can also define the density, rho A and rho V. And
Yes.
then if you work out the equation of motion for that, do you arrive at the continuity equation for rho and rho V separately? Do they all obey their own continuity equation?
Well, the continuity equation will give you the spatial component of the symmetry, right?
Yes.
So that we did work out, but you wouldn't be able to tell the other charges by doing that, right?
Yeah. Because in your theory, QV, the time derivative of QV is 0, time derivative of QA is 0. So in terms of the continuity equation language, they should satisfy their own individual continuity equations.
That's correct. There's no mixing.
Cool. Thank you.
Yeah. All right. Okay, so I have just defined infinitely many conserved charges on the lattice. For n of order 1, these are sum of local terms, but when n is of order L, this becomes highly non-local. In fact, these conserved operators, they generate an algebra that was first studied by Onsager in his original paper solving the two-dimensional Ising model in 1944. And this algebra was known as the Onsager algebra in the literature. And here it is. This is the algebra they form. In fact, it can be shown that the entire Onsager algebra can be generated by Q0 and Q1, namely our vector and axial charge. And G1 is the non-zero commutator on the right-hand side of the commutator of QB and QA. So we start with two symmetries that are very local. QV, which is the same as Q0, acts entirely on site. QA is locality preserving. It's not quite on site, but it only mixes the fermion with its nearest neighbor. But the moment you take commutator between them, the right-hand side will become more and more non-local. For Qn, you can show that as you take the continuum limit, it becomes QV when n is even, it becomes QA when n is odd. Q0 and Q1 are just two examples. In this limit, I'm fixing n to be order 1 and take L to infinity. On the other hand, Gn goes to 0 as you take the thin limit. So this entire Onsager algebra, as you take the continuum limit, just collapse to U1V times U1A. All right, so let me summarize what we have so far. I have realized an axial charge that's exactly conserved on the lattice. This charge actually has featured very briefly in these two papers from 30 years ago, but it was not interpreted as an axial lattice charge. This QA has integer eigenvalues. It's a locality preserving U1 lattice symmetry. The only thing we give up on is that it doesn't commute with the vector charge. And on the lattice, they form an Onsager algebra. Now, you might be wondering, maybe we're just stupid for not finding another axial charge that has an integer eigenvalue and also commute with the vector charge. In fact, in this model, there is a conserved lattice, another conserved quantity, which I call Q tilde A. This was first discussed by Banks, Kogas, and Susskind. This charge also commutes with the Hamiltonian. It's a close cousin of this. In fact, this can be written in terms of elements in the Onsager algebra. This symmetry does commute with the vector charge. However, it does not have integer eigenvalues. And it's not a coincidence that we couldn't find a charge that has integer eigenvalues and commute with the vector charge. And there are various no-go theorems stating this. One version of the no-go theorem was clearly spelled out in this recent paper by Nikita and Anton. Roughly, the statement is that you cannot have a left-moving U1 symmetry that has quantized eigenvalues. You see, here we mostly talk about QB and QA. If you want to get a left-moving U1 charge, you have to take their sum. But since QB and QA are non-commuting matrices, their sum, even though individually they have integer eigenvalues, their sum will not have integer eigenvalues. So in neither case can we construct a left-moving U1 symmetry with integer eigenvalue. And that's why it's consistent with the no-go theorem proven in the literature. This is also closely related to the Nielsen-Ninomiya theorem. Okay. All right. So now we have realized the symmetries actually in two different ways on the lattice, a quantized charge versus an unquantized charge. But you can ask,
could I ask a question before you continue?
hi.
In these old papers, why, if this charge that you've discovered was mentioned, why wasn't it taken more seriously? Do you have any?
What would I know?
I mean, how did they discuss it? In which context?
They talk about, okay, so the way they think about it is that, you know, they have a detailed map between the lattice degrees of freedom and the continuum fields. And they follow that maps to write down various continuum operators in terms of the lattice operators. So what they did is that they actually wrote down the density, the local term here of Q tilde A on the lattice. But they somehow didn't think about it as an axial global symmetry. They didn't think about it as an axial charge. They talk about the current. Yeah, and I talked to some of the authors. They didn't seem to have remembered this particular fact they had in their paper from 50 years ago. But I think that's natural. I don't even remember my own paper from 5 years ago. So
And another question, this Q tilde A,
yeah.
what does it correspond to in the continuum?
Oh, so both QA and Q tilde A in the continuum correspond to the same axial charge.
But QA is not integer quantized. Does it become integer quantized in continuum somehow, or?
That's right. So Q tilde A does not have integer eigenvalues, but as you take the continuum limit, the eigenvalues become integers.
Okay. Thank you.
Yep. Okay, any other question before I proceed? Great. All right. So we talk about axial symmetries on the lattice, but in the beginning, I said that in the continuum, there's an anomaly between the axial and the vector symmetry. So it's natural to wonder, is there something like an anomaly on the lattice? Well, anomaly is kind of a touchy word in our community. I think if you grab two different people on the street, they will give you two completely different interpretation or use of the word anomaly. So let's ask a more pragmatic question. What are the consequences of this lattice symmetries we found on the lattice? Now, what we showed is that any Hamiltonian, any local lattice Hamiltonian that commutes with the QV and QA symmetries must necessarily be gapless. So I started the talk by talking with this free fermion model. And that model has QV and QA as their symmetries. But you can ask, what are the more general Hamiltonians that are also invariant under QV and QA? And what we are able to show is that any such Hamiltonian must necessarily give you a gapless spectrum. So for those of you who haven't thought about lattice system a lot, by gapless, it means the following. So you take any finite L, the Hamiltonian is a matrix. You can diagonalize it on Mathematica. It will give you some discrete spectrum. By gapless, the question is, as you take L to be larger and larger, does the energy gap between the ground state and the first excited state, does that stay as order 1, or does it go to 0 as L goes to infinity? If the energy gap goes to 0 as L goes to infinity, we refer to that as a gapless spectrum. Okay. Now this consequence is very reminiscent of the consequence of a perturbative to Hoof anomalies of continuous global symmetry in the continuum field theory. So in this sense, we have some kind of anomaly on the lattice. And in condensed matter physics, this kind of anomaly is usually referred to as the Lipschitz-Matthias type anomaly, or LSM anomaly. So here is a snapshot of a phase diagram that we study of models preserving both QB and QA. So there are infinitely many Hamiltonians enjoying the symmetries. Here is just a two-dimensional slice. On this entire phase diagram, every point is gapless. There are some relativistic CFT points which we mark. These are some Wess-Zumino-Witten model. Then there are also some interesting Lipschitz transition between different part of the phase diagrams. All right. So that's all I want to say about the fermion model in 1+1D. This model is closely related to a boson model of spin chain.
Shu-Heng, can I ask a question about that fermion model?
Yeah,
About
please.
the anomaly matching part?
Yeah.
So, yeah, maybe if I remember correctly, what you have actually shown is that with QB and QA, Hamiltonian has to be quadratic in fermions, and you get gapless
That's right.
spectrum because of that. And compared with anomaly matching in continuum, it seems to be much stronger because, for example, in the case of continuum, we can have string vector current type interaction, still gapless. And do you understand why this difference appears?
Well, it's an excellent question. I understand might be too strong a word, but I can tell you why it has to be the case. So let's take the four Fermi interaction you mentioned as a specific example, right? So in the continuum, there's a four Fermi interaction that preserves both the vector and the axial U1 global symmetries. Now, the four Fermi interaction has a very natural lattice counterpart, but that lattice four Fermi interaction actually breaks our QA. Now, why is that the case? Now, I can tell you why why QA has to be broken by the four Fermi interaction. The reason is because we know the phase diagram of this lattice model deformed by the lattice four Fermi interaction, right? It will be gapless for some region, but then all in a sudden there will be a BKT transition going to a gap phase. But our theorem just shows that the model with these two symmetries have to be gapless, and therefore the four Fermi interaction cannot possibly be QA invariant. Otherwise, I can continuously take my model to a gap phase. Now, in addition to that, I'm not sure if I can say I have a better understanding. It's just quite common that, even though the lattice four Fermi term goes to the continuum four Fermi term, the symmetry they preserve might be very different. But I see you have a follow-up question, or
Yeah. So here you are basically saying that with introducing four Fermi interaction, then in bosonized side, cosine type interaction could become relevant because of the changing of the radius of compact boson, and you would eventually get a gapped phase. Is that what you are just saying?
Yes.
But if we really in a continuum current interaction, axial symmetry itself exists, so that relevant perturbation itself is forbidden by symmetry, right?
That's right. That's right. So in the continuum, you have an entire line of conformal manifold.
Yeah.
But on the lattice, without knowing this QA, we know the phase diagram has a
yeah. Okay, I see.
So that tells you that this QA has to be special on that parameter.
I see. Right.
Yeah.
But is there any chance that there is a nice closed subalgebra of your Onsaga symmetry such that kind of counterpart of four Fermi or higher order interaction could become?
Excellent question. Yeah, excellent question. Maybe we try. We haven't figured that out. Yeah.
Okay. Maybe very interesting. Okay, thank you.
No, I think it's very interesting. Yeah, we just somehow couldn't find it. Yeah.
Sorry, just a follow-up question. So is it correct to say that, I mean, you can't write any operators which are exactly marginal here? Or do you have, I mean, on the lattice, why wouldn't you be able to write operators which preserve both of these symmetries?
So I think these are two related but different questions. So on the lattice, there is a four Fermi term you can write down.
Right.
And that does flow to the continuum to the four Fermi exactly marginal deformation. However, that lattice four Fermi term breaks the lattice QA.
But I'm asking, can you write any non-trivial term which does not break the QA on the lattice? Anything else?
I could. So you could, but they're not interacting. They have to be quadratic. That's something we prove.
I see. They're all quadratic. But you can then explore this whole conformal manifold by adding such terms, can you? I mean, do they flow to the correct?
So that's what so this is a slice of the manifold.
Okay.
Yeah.
So you can access only the slice, or can you access everything?
Oh, we can access everything. It's just because it's quadratic, it's exactly solvable.
Okay.
So you can literally write it down. Here I only present the two-dimensional slice, but I can also present the three-dimensional slice if I want to, or more. Yeah.
Okay.
But most of the points are non-relativistic, so it's a little bit hard to think about. Well, some of them are easy to think. Some of them are just changing some relative velocity between the left mover, the bit of the fermions.
Okay, thank you.
Mm-hmm. Okay. All right. So That's the fermion model. There's a closely related spin chain model known as the XX model, or sometimes also called the isotropic XY model. So this X are poly X and Y is a poly Y operator. This model is locally equivalent to the free fermion model we were talking about, but globally they are different. This flows to the C equals to 1 compact boson CFT at a particular radius. Now, this model in the continuum has two U1 symmetries, similar to the vector and the axial symmetries. In string theory, these two U1s are called the momentum U1 and the winding U1. On the lattice, this model manifestly realized the momentum U1 symmetry Qm, but the winding U1 is obscure. So in these papers and also in our second paper from last year, we realized the winding U1 symmetry exactly in this lattice model. Now, in the fermion case, if you remember, the two U1, the vector and the axials, are exchanged by a Majorana translation that only shift the B fermion. The counterpart of that in this bosonic model is a non-invertible symmetry, which I call D. So this non-invertible symmetry doesn't have an inverse, and as you push your momentum charge Q through this non-invertible symmetry, it becomes the winding charge. There's an important factor of 2, but let me not say too much about it. In string theory, there's a T-duality exchanging the momentum and the winding, and you can view this non-invertible lattice symmetry operator D as the lattice counterpart that implements this T-duality. So usually we say that T-duality doesn't exist for the XXZ lattice model. It only exists in the continuum because on the lattice, we typically only have one U1, not two. And T-duality exchanges the two U1. So it's only emergent in the continuum. But here, we show that at this special point of the XXZ model, there's actually a lattice T-duality, and it's implemented by this non-invertible operator. Okay, so this is the one-slide summary of our second paper on this subject. All right, so if there's no more question, I'm going to depart from 1 plus 1D and go to 2 plus 1D. All right. In 2 plus 1D, there are two possible directions one can generalize our story. One direction is to assume that in 2 plus 1D, you still have discrete number of zeros in your dispersion relation. So they are called the Dirac point. This will be the case for graphene or for honeycomb lattice model. Alternatively, maybe the zeros of your dispersion relation forms a non-trivial curve in your brilliant zone. That's known as the Fermi surface. Today, I'll talk about the first scenario because the first scenario, I think, is closer to high energy physics, whereas Fermi surface is much more subtle. So what's the model we are going to consider? The model is going to be a 2 plus 1D honeycomb lattice model. It's a toy model for graphene. And the UV Hamiltonian is again similar to what we had in 1 plus 1D. We put a single complex fermion at the site of your honeycomb model. There's a closely related model you can consider, which is to work on a square lattice, but with a non-trivial staggering. That's also known as the stagger fermion model. But today, let me focus on the honeycomb model. In some way, the honeycomb model is actually easier than the stagger fermion model. Okay, so let me just start with this Hamiltonian. Is qualitatively the same as the one in 1 plus 1D. You might notice that there's no I, but that's just a matter of convention. And this bracket means that I only include terms that involve nearest neighbor interaction. So blacks talk to white talks to black, but there's no next to nearest neighbor interaction. So this is the UV lattice Hamiltonian. What is the IR Lagrangian? The IR Lagrangian this time is two massless Dirac fermions. Okay. So this time we actually have a doubling problem. This model is not a problem because there are other ways to fix it, but let me just say that the very naive nearest neighbor Hamiltonian, this one given here, will give you 2 massless Dirac fermions rather than 1. And I'll say more about why that is the case. Okay, but this is a well-known fact. I think this is something everyone learns in solid state physics. So what are the UV and the IR global symmetries? This is the UV lattice model. This is the IR free Dirac fermions. So A and B's are just the labels for these 2 species of fermions. There's no sum in A. A is not an index, sorry. So in the UV, there's a U1 global symmetry that rotates every complex fermion by a phase. That's the analog of the U1V we had in 1+1D. In the IR, we have 2 species of Dirac fermions, so I can rotate them by a SU2 matrix. In fact, the symmetry is even bigger. You can decompose each Dirac fermions into 2 Majorana's, and then the global symmetry is O4. But today, let me just focus on the SU2 subgroup of O4. So in 2+1D, this symmetry mismatch between the UV and the IR is even sharper. In the UV, you have a single U1. In the IR, you have O4, or rather, I would like to just focus on the SU2 subgroup. So the question is, where is the SU2 symmetries on the lattice? So the SU2 will play the role of the U1V times U1A in our previous talk, previous part of the talk. So if you draw the dispersion relation of the honeycomb model, you'll see that the 2 bands will touch at 6 different points, but many of them are identified. So eventually there are just 2 zeros. This one labeled by K, this one labeled by K prime. All the other points are identified. So these 2 points are the analog of our K equals to 0 and K equals to L over 2 in part 1 of the talk. So again, you have zeros at 2 different locations in momentum space. Each one of them gives you a single Dirac fermions. The manifest U1 rotates to 2 Dirac cones by the same phase. The SU2 would rotate the 2 Dirac cones. So the question is, do you have a locality preserving symmetries that does that on the lattice? Okay, is the setup clear to everyone? Great. Now, in 1+1D, the difficulty for realizing such a axial symmetry is because of the Schringer anomaly. In 2+1D, or in any odd spacetime dimension, there's no perturbative anomaly. The counterpart of the perturbative anomaly is replaced by the parity anomaly. Now, parity anomaly is really a misnomer because parity typically refers to symmetry that reflects all the spatial coordinates. But here in 2+1D, parity should really be replaced by reflection. But because of historic reason, we still call it parity. But for the sake of this talk, you can just think about it as a time reversal anomaly. So this is anomaly. You can think about it as a mixed anomaly between the SU2 flavor symmetry I just mentioned and the time reversal symmetry. This was first discovered by high-energy physicists in the 80s, and later on play a very important role in condensed matter physics, such as in the context of topological insulator. So what does the parity anomaly mean? It means that if you couple the theory to the SU2 background gauge field A mu, then the partition function is not time reversal invariant. So this is the partition function coupled to the SU2 background gauge field. And if you do a time reversal transformation, it picks up a phase. And the phase is given by the eta invariant. Okay, don't worry too much about the eta invariant. It's related to the Chern-Simons action, but I'm not going to get into the details. Okay. Now, for most of you in the audience, maybe you have heard about parity anomaly in the context as an anomaly between time reversal symmetry and the U1 global symmetry. That is the more famous parity anomaly, and that already exists for a single Dirac fermion. But that U1 parity anomaly doesn't exist in our model of the honeycomb lattice model because we have two Dirac fermions. Rather, what we are going to shoot for is the SU2 parity anomaly. So it's a slightly advanced version of what people usually think about. Okay. So following the same prescription we had in 1+1D, we also find an Onsager algebra on the lattice for this for this nearest neighbor lattice model on a honeycomb lattice. The trick again is to decompose the complex fermions into real Majorana pairs and utilize the lattice translation symmetry. There's one slight difference is that in 1+1D, you just have one lattice translation, one direction for the lattice translation. Now on honeycomb lattice, you have two directions. You can translate, you can translate in the A1 direction, or you can also translate in the A2 direction. These are these two orange arrows on the lattice. So in the end, in addition to the manifest U1 global symmetry, you also get two more generators, which I call QAI. This could be QA1 or QA2. A1 and A2 are these two vectors on the lattice, and these are the two Onsager charges. They have integer eigenvalues, just like our QA in 1+1D. They commute with the Hamiltonian. The only catch is that they do not commute with Q. And as you can see, if you multiply the two terms, you will have some CC term and C dagger term. All right. Now, how do you visualize these Onsager charges? Remember, in 1+1D, the QV and QA give you the U1V and U1A, and the continuum is U1V times U1A. Here, these Onsager charges in the low energy will give you three U1 rotations inside the SU2 group. So what are the three directions? You can take Q, the original manifest U1, to be along this sigma 2 direction, the y axis. This is a rotation here. Then QA1 and QA2 will be these two angles. These three arrows are coplane, and the angle between them is 2 pi over 3. So if you take any pair of them, you will be doing a rotation here or doing a rotation here. And by composing them, you generate the entire SU2. So in 1+1D, the slogan was that we find the axial symmetry arising from the Onsager algebra. In 2+1D, what we found is that the SU2 symmetry, which is usually called the valley symmetry in condensed matter, because you can see these are two different valleys of Dirac cones. So valley symmetry is that means that you are rotating between the different valleys. So in 2+1D, just one second. In 2+1D, the slogan is that we find the SU2 valley symmetry arising also from the Onsager algebra. Yes, please.
So this thing QAI, so I guess
Yes.
there's QA1 and QA2.
Correct.
They also commute with the lattice Hamiltonian, C dagger
Correct.
R, C R prime. So I guess maybe you can define a corresponding current or current density vector.
Yes. Yes.
And then you can talk about coupling that to an appropriate, perturbation, try to calculate the response functions and calculate something like conductivities by feeding through the Kubo formula. So you can actually come up with a whole variety of sort of transport coefficients.
Yes. So we thought a little bit about that direction, not a lot. So the short answer is that we don't know yet, but I suspect because it's unitarily related to the original Q, most of the quantities will be the same as the manifest Q. But there are some other things that we want to compute, but we haven't had any concrete result.
I see.
Yeah, but in the paper we did compute both the time component and the spatial components of the current.
Hi, Shu-Heng.
Yes.
It's Tin. Just to make sure I understand. So your statement is that in the continuum limit, this forms an SU2
Right.
algebra. Whereas when you're on a finite lattice, it's something more complicated. It's a Onsager algebra.
It's an Onsager algebra, yes.
And I mean, is there a notion still of some continuous like object like SU2, or could you? I mean, is there an analog in the
Yeah, there might
Onsager
be.
of
I mean,
SU2?
there is some notion of Onsager group. I mean, you can naively just exponentiate the charges. It's more direct to compare the Lie algebra,
Right.
right? So SU2 has 3 generators. Onsager has infinitely many of them. As you take the continuum limit, that infinite family of Onsager charges collapse to 3.
Well, in this case, though, you don't have so much of a problem that they don't commute. They don't commute.
That's right. That's
in the
fair.
SU2.
That's fair. That's right. Yeah, that's right. But you can see on the lattice that they do not form an SU2.
Right.
Or in other words, you have to have infinitely many of them to close the algebra. Whereas for the SU2 algebra, the 3 of those guys already close.
Thank you.
Sorry, I have a question. So the Onsager algebra in 2+1D and in 1+1D are different Onsager algebras, right? Or are they the same Onsager algebra?
Good. The short answer is that they are basically the same.
Then does it mean that in 1+1D model, there is still a SU2 symmetry somehow in the continuum?
No. So it's the same lattice algebra, but depending on the space-time dimension and the Hamiltonian you choose, that same lattice algebra can become different continuum symmetries. Right? This is quite common, right? Even just in 1+1D, if you have a lattice translation, depending on the Hamiltonian, the lattice translation can become a trivial symmetry in the IR, or it can become internal Z2 symmetry in the IR. And similar thing is happening here.
I see.
But here it's even more drastic because these are between different dimensions.
Yeah, okay, thank you.
It will be even more dramatic when I get to part 3. Okay, so yes, indeed, the upshot here is that the SU2 valley symmetry of the continuum Dirac free fermion theory arises from the Onsager algebra. All right. Now, again, you can ask, is there a parity anomaly on the lattice? This SU2 valley symmetry has a mixed anomaly with the time reversal symmetry. Now, on the lattice, we prove a similar statement as in 1+1D. We prove that any local Hamiltonian that commutes with the Onsager symmetry and spacetime reflections must be gapless. So this could be a reflection in space or a time reversal symmetry. And you can test this statement we prove on some simple model. So you can take the original gapless Hamiltonian with nearest neighbor interaction. You can add this deformation. This is the on-site deformation. R and R on the same side. This is sometimes people call this the stagger chemical potential. This was first discussed by Semenov in '84. This essentially give the continuum Dirac fermion a mass. This turn breaks the Onsager symmetry but preserve time reversal. And indeed, the low energy phase is gap. This is consistent with the fact that you break the Onsager, so there's no more anomaly. Alternatively, you can add this next to nearest neighbor interaction, studying the famous paper by Hodan. This term preserves the Onsager symmetry. However, it breaks time reversal. Therefore, this also drives you to a gap phase. The simplest non-trivial deformation that preserves both Onsager and time reversal is this next to nearest neighbor interaction. And this preserves both of them, and it is gapless, and it has an interesting phase diagram that we study in the paper. But I will not say too much about it during the talk. So this is just a simple demonstration of various deformations. Some of them break the symmetry, some of them preserve the symmetry, and how the resulting phase diagram is consistent with the anomaly constraint we prove.
Is there a like do you know the continuum limit of the third line?
Right. So let me try to recall. I think the short answer is I don't think it's a relativistic relevant deformation. So the short answer is no. It kind of changes the dispersion relation to something non-relativistic.
Thanks.
It's somewhat similar to the 1 plus 1D story. All right. Okay, so let me quickly summarize part 1 and part 2, and I'll make some concluding remark for in 3 plus 1D. So in part 1 of the talk, this is the lattice Hamiltonian we start with. This is in 1 plus 1D. The continuum theory is a free Dirac fermion with a left mover and a right mover. And we found that in addition to the manifest vector U1 symmetry, there's an exact axial U1 symmetry. Both of them are conserved quantities on a finite lattice. The only catch is that they don't commute and they generate the Onsager algebra. And you can say that the Schwinger anomaly of the continuum Dirac fermion field theory arises from this non-abelian Onsager algebra. Is there an anomaly on the lattice? Well, that depends on what you mean by the anomaly. What we showed is that the lattice symmetries QV and QA force the Hamiltonian to be gapless. You might also ask whether or not there's an anomaly in the following way. In the continuum, one way to detect the anomaly is that if you gauge the vector symmetry, then the axial symmetry is gone. So you can ask, does the same thing happen on the lattice here for our QV and QA? The answer is yes, but for a slightly different reason. QV and QA do not commute. So the moment you gauge QV, Gauss's law will automatically break QA for you. This is like in the continuum if you have a SU2 global symmetry and you gauge the U1Z subgroup. But the moment you gauge U1Z subgroup, U1X is broken. But it's not for any deep anomaly or a dimension regularization reason. It just follows from the fact that the algebra is non-abelian. And this is how it happens for the Onsager algebra. So you can say that the input and the output are similar to the anomalies in the continuum, but the mechanism is different. Yes, Sang-Woo.
Yes. Sorry. Can you remind me if QA or in continuum limit rather, U1A has a self or diagonal anomaly itself?
Thank you for the question. I should have clarified that in the beginning of my talk. So the answer is no. One very easy way to see that is that, as I emphasized in the continuum, QV and QA are unitarily related.
Right, I see.
The anomaly structure is the same.
Okay, that
So
makes sense because at some point you mentioned if you gauge either of the two, you have a vice versa part. I was a little bit confused, like in the 3 plus 1D case, but okay, that clarifies.
That's right. So this is something qualitatively different between 1 plus 1 and 3 plus 1.
Got it. Thanks.
QA 1 plus 1 actually has no anomaly.
Okay.
And that's why we can realize QV and QA separately without any trouble on the lattice. There's an issue only when you put QV and QA together side by side.
I see. Even though the unitary relation between the QA and QV seems to be valid even as a 3 plus 1D expression naively, because you just need to flip the phase factor.
That's actually wrong. That's
see.
actually wrong.
Really? Okay.
And say a little bit about that later.
Okay, cool. I will wait. Thanks.
Okay. This is 1 plus 1D. And in 2 plus 1D, we studied the same nearest neighbor Hamiltonian on a honeycomb model. The continuum limit is 2 Dirac fermions, which has a SU2 valley symmetry. And it has a parity anomaly with time reversal symmetry. What we show is that the parity anomaly can also arise from the same non-abelian Onsager algebra. And now moving on to 3 plus 1. Okay, so there was a very nice paper from earlier this year. They discussed 2 lattice fermion models in 3 plus 1D. The first model flows to a single massless Dirac fermion in the continuum. Okay, it's an unpaired Dirac fermion. This lattice model also has an Onsager symmetry, which becomes the SU2 flavor symmetry of the Dirac fermion in the continuum. So let me remind you, in 3 plus 1D, if you have a single Dirac fermion, that's 2 vials. So we are in a similar situation. And 2 vial fermions will have a U2 global symmetries rotating them. The U1 part of the U2 is the axial U1 that has a self-anomaly. That part they didn't realize, but they realized the SU2 part, which famously has the Witten anomaly. And this SU2 also arises from the Onsager algebra. So if you put all 3 examples together, there's an interesting coherent picture. There's a single lattice algebra discovered by Onsager in 1944. If you pick the 1 plus 1D lattice Hamiltonian, that goes through the Schringer anomaly. And that goes through the U1V times U1A symmetry in 1 plus 1D, which counts with the Schringer anomaly. If you pick a different Hamiltonian in 2 plus 1D, that goes to a SU2 valley symmetry, which has a parity anomaly. And if you pick yet another different Hamiltonian in 3 plus 1D, that goes to a SU2 flavor symmetry in the continuum that has a Witten anomaly. So somehow this Onsager algebra governs 3 different kinds of anomalies. All right. Now, this paper also discusses another model which flows to an unpaired massless vial fermion in the continuum 3 plus 1 in 3 plus 1 in continuum field theory. So that sounds a little bit puzzling because earlier in this talk we mentioned the fermion doubling problem. But that was in 1 plus 1D. In 1 plus 1D, it's not possible to realize a single left-moving vial fermion. In 3 plus 1D, the statement of the fermion doubling problem, in my opinion, has been misinterpreted in the literature a lot. And that leaves room for actually a lattice construction for a single vial without violation of any known no-go theorem. The hidden assumption that was made in all this no-go theorem is that they assume a U1 global symmetries that's realized in the lattice model. So a single vial fermion has a U1 global symmetry. If you assume you have that U1 global symmetry, then there's a no-go theorem for the fermion doubling problem. But there's no fermion doubling problem if you're willing to give up this U1 global symmetry, and that's exactly what this paper did. So if you compare the 1 plus 1D with the 3 plus 1D story, in 1 plus 1D, there are 2 kinds of vial fermions. They have different Lagrangians. A left-moving vial fermion has this Lagrangian with a plus sign here. A right-moving vial fermion has this Lagrangian with a minus sign here. There is no field redefinition you can relate one to another. These are 2 distinct representations of Lorentz group in 1 plus 1D. Relatedly, a single left-moving fermion has a pure gravitational anomaly. And that's related to the reason why an unpaired vial fermion cannot be realized on the lattice. In 3 plus 1D, related to Songwoo's question, it's entirely different. There's only one vial Lagrangian. And it involves both psi and psi dagger. If you go to any quantum field theory textbook, this is the one and only vial Lagrangian. So without specifying any global symmetry, there's no notion of a left-moving vial fermion versus a right-moving vial fermion. If you open Srinicki's textbook on quantum field theory, every vial fermion is a left-moving. So the statement of the fermion doubling problem only makes sense when you specify a global symmetry. Related to that, there's a U1 gravitational anomaly in the single vial fermion, but there's no pure gravitational anomaly. And that's why an unpaired vial fermion can be realized on the lattice at the cost of giving up the U1. And this has been known in the context of vial semi-metal for some time in the condensed matter physics literature. Okay. What was new in this new paper is that even though they didn't realize a U1 global symmetry, their model has an unquantized conserved charge Q tilde, which does compute with the Hamiltonian but does not have integer eigenvalues. And this is related or reminiscent of the unquantized charge we have in 1 plus 1D as well. In both cases, this unquantized charge generates an R global symmetry rather than U1. And for a reason I don't fully understand, that's the mechanism how you evades the no-go theorem by Nielsen and Ninomiya. All right, I think that's all I want to say today. So maybe in my last slide, I'll just repeat this picture for the Onsager algebra. All right, thank you for all the questions and attention.
All right, thank you so much for a great talk. So time for questions.
At the end of your 1 plus 1D discussion in the context of the XX Hamiltonian, you mentioned the existence of some non-invertible symmetry D. I didn't quite catch the importance of that. Is it related to the rest of your discussions in the 1 plus 1D fermion model, or is it something?
In a way, yes. So this equation at the bottom is related to this equation in the fermion model. So in the fermion model, QA and QV are related by a Majorana lattice translation, which is invertible. But when you bosonize the system globally in a careful way, this Majorana translations becomes a non-invertible symmetry. This is the bosonic counterpart of the story. In fact, in our own reference frame, I was telling this story in an entire backward manner. The way Sal, Arco, and I started this project is that we first realized that there's a non-invertible symmetry in the XX model, which should satisfy this relation. And then we realized that there's a winding symmetry on the lattice for the XX model. And then we realized that that implies there's an axial U1 symmetry in the fermion model. And then we say, stop, that's actually the interesting part of the story. Let's write a paper about that first.
So there's no interesting physical consequence associated with the existence of D in the HXX, or?
Oh, there is. So there are you can talk about deformation of the model, preserving D, but perhaps breaking some of the other symmetries. And then you can show various LSM type constraints, as we did in that paper.
Okay.
And another interesting aspect is that this D is the lattice operator that implements T-duality on the lattice.
Okay, thank you. When you discuss 1 plus 2 dimension, if I look at the IR limit with continuum field theory, time reversal symmetry and the parity symmetry are in equal footing after Euclideanization.
Yes.
However, if I look at the lattice models in UV, then how can I understand such formal equivalence in lattice model?
Right.
Time
So
reversal.
it's a good question. So first of all, we don't claim that parity. I should really say reflection. Let me say reflection. It's not parity, because parity will flip X and Y at the same time. But here it's important that you only flip one out of the three space-time coordinates. So on the lattice, we don't claim reflection and time reversal are on the same footing. We prove our LSM type constraint separately for for all kinds of space-time reflection. And it is it's a very interesting question to see why time reversal and reflection are become on the same footing in the continuum limit. but I don't think there's a general understanding of how that works. In actual model, in specific model, you can, such as the free fermion model, here you can map everything explicitly. But on general grounds, how does Lorentz symmetries emerges? How do the Euclidean structure of the quantum field theory emerges? I think that's a deep question, and I don't have a better answer to give at this point.
Thank you very much for a very, very good talk, interesting talk. My question is, so for today, you focused on fermion anomaly, especially related to the continuous symmetries, and therefore anomaly matching suggests that, anomaly matching directly point to the gaplessness of the infrared phases. And there exist other symmetries, such as discrete symmetries, and then anomalies, which can also be matched by, not by the gapless mode, but by, say, symmetry preserving TQFTs. And first of, in that case, I don't even know what will be the lattice statement that one can come up with to translate the continuum version of an anomaly matching statement in terms of TQFT into a lattice version. And I wonder if there has been any progress towards this direction.
So that's a very nice comment, because we also made a similar comment in our paper that if you look at this slide, you can ask, what is the common feature of these three anomalies? And one common feature is that none of them can be matched by a topological quantum field theory.
Right.
Now, if you ask me, when we set up the problem, that we didn't have this in mind. This seems to be a coincidence that we found. So we don't have a deep understanding why the anomalies arising from the Onsager algebra can never be matched by a TQFT.
Okay, I see.
Having said that, there are many other anomalies that you can realize in a much more straightforward way on the lattice, and some of them can be matched by TQFT. I think the novelty of this construction is that this anomalies that cannot be matched by TQFT in a way, especially perturbative anomalies, are much more subtle, and they are much more, maybe subtle is not the right word, because they are straightforward from the continuum point of view, but they seem really severe from the lattice Hamiltonian point of view if your local Hilbert space is fine dimensional. So yeah, I think the novelty of this series of work is that we're trying to realize all these more severe anomalies on the lattice at the cost of modifying the algebra for the symmetries.
Right, but then do you have a proper pseudo statement for a anomaly matching in terms of TQFT in a lattice language? So in the lattice language, your statement or your way of proving the truth anomaly is not by explicitly sort of computing the anomaly and so on, but by showing that such a thing has to be gapless, right? But then if there is any discrete symmetries or any such of an anomaly which can be matched by TQFT, what will be the analog or corresponding statement in terms of lattice?
Well, I have to say that even if you don't talk about TQFT, there is an even more embarrassing aspect of the story that we were not able to probe. So if you go to 2+1D, parity anomaly can be matched by a gapless phase, but it can also be matched by a spontaneous symmetry breaking phase.
That's true. Yes.
So you can also call that TQFT if you wish. That's fine.
Right. That's true.
But we don't know how to realize that phase from this particular microscopic
I see. Okay, I see.
Yeah.
Right.
It is a gap in our understanding. It's not a contradiction of any sorts, but we just don't know how to realize it.
I see. Got it.
Related to that, if you replace the Valley's SU2 symmetry by U1, U1 parity anomaly can be realized by TQFT, but we don't know how to realize it using the Onsager algebra. Probably it cannot.
Oh, okay. And I understood your previous statement better now. I see. Somehow Onsager algebra and the associated anomaly, even though from a continuum picture, it can be matched by TQFT, somehow it only realizes the matching in terms of gapless mode. That's
yeah. But that might be the restriction of the class of models we restrict ourselves to.
Okay, thanks.
Hi, Shu-Heng. I have a question.
Yeah.
So suppose that suppose that we have a continuous theory, some model in the continuum limit, which has two global symmetry, and this two global symmetry has a mixed anomaly. And then think
Right.
about the lattice model, and suppose that we can find the charges, corresponding charges in the lattice model. Do you
Right.
expect that this charge will not commute with each other
I
always?
think no, I wouldn't say always. I think it
Okay,
depends. It depends on the details of the mix anomaly.
I see.
So
What kind of detail are you talking about?
I don't have a general I don't have a general statement. I know a handful of examples.
I
So
see.
for instance, it could be that you have a Z2 symmetry and a Z2 cross Z2 symmetry with a mixed anomaly. For this kind of anomaly, it's very easy to realize then without changing the algebra.
Does it because the theory in the even in the continuum limit, maybe in the IR limit, do we have a baseless fermions there or?
So the example I had in mind doesn't even require fermions. It's an excellent question. Your question is what kind of anomalies can be realized in, say, a lattice model with fine-dimensional local Hilbert space? And no one has a complete answer as far as I know. And indeed, I think part of the goal of this work is try to provide some examples in this direction.
Yeah,
But
thank
so
you.
far, I think most of the analysis are very much based on examples.
Hi, Shu-Heng.
Yeah.
So correct me if I'm wrong. Did you mention that for the honeycomb lattice, there's a way to realize a single Dirac fermion?
Oh yeah, that's right.
So how do you do this? And
That's actually not me who did it. That was that was one of Hoden's work from this paper.
and I see. So I see. So, but that doesn't have time reversal. That's what you're saying.
That's right. Yeah.
I see. Okay.
So the trick is to turn on both of these terms and tune their coefficient to a specific value.
I see. But
Yeah.
there is no, to your knowledge, way to do this with keeping time reversal. Because that's the interesting problem, right?
Yeah. No, but let me think about it for a second. Yeah. So there's definitely no way to do it while keeping both the U1 and the time reversal.
Right.
So let me try to recall. So this model preserves U1, right? If you only have the first two terms plus the ordinary nearest neighbor, this model preserves U1. But the continuum limit of a single Dirac fermion has a U1 parity anomaly.
Right.
So if you have the U1 on the lattice, that means you have to give up on the time reversal. But I think there's also a way to do this while sacrificing the U1. There might be a way to do it. Maybe it's in our paper. I don't remember
But
top of my
I don't understand. The anomaly is a 't Hooft anomaly, right? It's a 't Hooft anomaly in the continuum.
Right.
So
Yeah.
the question is whether we can ever realize this on the lattice. Is it your opinion that it's just impossible or we haven't found it?
Yeah, you're right. So in my reasoning, I kind of assume such a 't Hooft anomaly cannot be realized on such a lattice. As far as I know, there's no such a proof for U1 parity anomaly. But I somehow believe that's a true statement. It would be interesting to prove it. What I can say is that in 1 plus 1D, there are rigorous proofs that you cannot realize the self-anomaly of a left-moving U1 symmetry.
Well, this is partially because of the pure gravitational anomaly, or maybe entirely, right? That's at least my take in 1 plus 1D. Whereas in 2 plus 1D, I don't see that obstruction. It's not as severe, at least. So,
well, but it's similar to the 3 plus. There's also a similar no-go theory in 3 plus 1D, right? The single Weyl fermion has a mixed anomaly between U1 and gravitation. And it has been proven that U1 cannot be realized on such a fine-dimensional lattice.
oh, really?
Yes, this is a paper by Lukas Witkowski and Chen-Ke Shu from 2023. So I think the status of that is similar to the U1 parity anomaly, right? U1 parity anomaly is kind of a mix. It's a mixed anomaly between U1 and time reversal. You can view time reversal as gravitational if you wish.
Right.
So I suspect there's a similar no-go theorem for the U1 parity anomaly.
Thank you.
Yeah. It's an interesting question.
Any more questions? Actually, I have one, a little philosophical, maybe closely related to someone's question. So I'm a little bit concerned that so in usual continuum field theory, like you don't really just match the symmetries, right? You match the anomalies to constrain the IR phase, right? So, but
Yeah.
in your setup, it seems that this Onsager symmetry and time reversal symmetry or parity or whatever is stringent enough already without any further like anomaly type constraints. So I'm a little puzzled by that. So does that actually include the like usual tooth anomaly thing?
So in 1+1D, there's no such issue, right? In 1+1D, in the continuum, you know the Schwinger anomaly can only be compatible with a gapless phase. This issue only arises for the 2+1D parity anomalies case. In 1+1D, there's no way to match the Schwinger anomaly by a gap quantum field theory.
Yeah, but in your like almost last slide is Onsager symmetry being seems like it that obstructs the IR phase. Sounds a little puzzling to me. So it's not just Onsager symmetry itself, or
Oh yeah. Okay, let me go to the last slide. This one.
yeah, I mean, usually like symmetry algebra is not enough to constrain. You got to feed in something extra on top of that, like the tooth anomaly.
Right. So I would say in this case, the anomaly, the symmetry operators are not. Okay, so let me put it this way. People usually say that let's focus on 1+1D because I think most of the statement carries over to 2+1, 3+1. In 1+1D, people usually say that the actual U1 symmetry QA is emergent. It's not an exact symmetry on the lattice. But our work is saying that that's not the case. QA is not an emergent symmetry, right? It comes from an exact symmetry operator on the lattice. Having said that, I'm not sure if I would say that the anomaly of the axial symmetry in the IR is emergent. So this operator on the lattice, it doesn't see the anomaly of the continuum theory. The anomaly only arises after you commit to a particular Hamiltonian. And this is a common phenomenon when you go from the lattice to the continuum. And let me again use the example of a lattice translation. Forget about all this Onsager nonsense. It has been known that in 1+1D, if you start with just an ordinary lattice translation of a qubit, that symmetry has no anomaly, right? You can write down a paramagnet Hamiltonian that's completely trivial, no degeneracy, completely gap, but still respect the translation symmetry. However, you can choose a different Hamiltonian, such as the Heisenberg spin chain Hamiltonian, such that this lattice translation becomes an anomalous Z2. So this is the most elementary example of an exact symmetry of the IR theory, a symmetry in the IR theory that arises from an exact symmetry on the lattice, and yet its anomaly is emergent. And I think Onsager algebra is like that. I think that's the best analogy I can provide, that Onsager symmetry is somewhat like a translation symmetry, lattice translation symmetry. It by itself doesn't have an intrinsic lattice anomaly, but it has room to realize different kind of continuum anomalies in the IR.
I see.
So I think I think I'm giving a too long an answer to a short question you ask. But I think the bigger philosophical point I want to convey is that when you are trying to match symmetries and anomaly between the continuum and the lattice, there are a lot more possibilities than you would have naively thought. And I think it's an ongoing, interesting research endeavor to figure out what are all the mechanisms on how the symmetries and anomaly can match between the lattice and the continuum.
All right. Thanks for the clarification. Okay, seems there's no more. Oh, there's one.
Sorry, I'm a little confused. So what's the precise definition of emergent symmetry and emergent anomaly?
Yeah, I didn't define them during the bulk of my talk because sometimes I do, but that would typically lead to a different discussion. So an emergent symmetry, let's start with what emergent symmetries means. An emergent symmetry is a symmetry that's never exact. So you start from the UV theory and you go to an IR theory. The UV theory could be a lattice, could be a continuum, doesn't really matter for the sake of this discussion. When you go from the UV to the IR, in the strict IR, you might have some symmetries that the UV theory doesn't have. And in emergent symmetry is a symmetry in the IR that doesn't come from any exact conserved quantity in the UV. Okay. But that's not the case for the axial symmetry here. The axial symmetry QA comes from an exact lattice operator in the UV. So in that sense, the the QA axial symmetry is not emergent. It's actually exact. Now, an emergent anomaly means that the lattice operator where this symmetries comes from does not necessarily have an intrinsic anomaly, meaning that you can choose a Hamiltonian that respects this lattice symmetry, and yet the low energy phase of this Hamiltonian is completely trivial. Yeah, it's a great question, but I'm afraid that this might requires a whole other lecture to really carefully explain
Yeah,
it.
but can I at least because I'm a little bit puzzled when you say that the anomaly, especially it's a toothed anomaly, is emergent. So then is the continuum limit not a small deformation or small small changes of the theory? You think that's radical big changes? Because it is well known that toothed anomaly should be invariant under small deformation, which is a symmetry preserving. And at least as you have shown that in the continuum under the continuum limit, Ansag algebra, which seems to be much larger symmetry than the symmetry we see in the continuum limit, therefore, at least it preserves the U1 axial part of the symmetry and U1 AV part of the symmetry. And yet, then how do I make sense that the toothed anomaly emerges rather than it should be there?
I think going from the continuum to the lattice is a very radical deformation.
Okay, so that's
right?
the answer.
Highly irrelevant deformation, right? So going from UV to the IR is straightforward. But if you want to go from the continuum back to the UV lattice, that's a highly non-trivial task.
Okay.
So that's why anomalies can sometimes be emergent.
Okay. All right, thanks.
All right. So even though Shu-Heng said that you didn't prepare for 2-hour talk, so you almost filled the time.
Thank you all for the question.
Thank you very much for a great talk. And let's thank Shu-Heng again.
Thank you.